Good afternoon, everyone. We are about to start. So today we have a pleasure to attend to the talk by Professor Jason Gao. Professor Gao did his PhD at UC San Diego and completed in 1989. Then for 2 years, from 1989 to 1991, Professor Gao was postdoc here, and then after that, joined the University of Carleton as a faculty member and was still some time here as visiting a professor. And yeah, today, welcome back.
Okay, thank you. So it's always nice to be back here. Okay, so today's talk involves two topics. One is about graph embeddings, and the second one is about map colorings. And these topics, of course, are closely related, as you will see. And so first of all, we're talking about graphs embedded on surfaces. So a surface here is just a two-dimensional manifold without a boundary. So here I give you two simplest examples. This one, well, the simplest one, of course, is the sphere, which has genus 0. Then the so-called orientable surfaces, right? This is the torus, which can be viewed as, obtained from this rectangle. You just identify the opposite sides. So if you identify this way, you get a cylinder, and then I identify these two holes, you get the torus, right, the donut shape. And in general, you can have an orientable surface of genus G, which is obtained from the sphere by adding sort of G handles to it. And then there's another type of surface, non-orientable. Right, this is the simplest one, denoted by N1. N is for non-orientable. 1 is the so-called number of crosscaps. Now, this can be viewed as follows. You just take a disk here, and then you just identify the antipodal points on the disk, okay? Then, of course, you cannot visualize this in three-dimensional space because it intersects itself, okay? And then you have N2 with 2 crosscaps. That's equivalent to, well, that's usually called a Klein bottle, okay, which can be obtained like this, but this side, you just take the opposite direction, so you have to take a twist. So according to the classification of surfaces, right, all two-dimensional manifolds belong to these two types. And now here is an example of a graph embedded on the torus here, which is called a map. First of all, there's no edge crossings. Secondly, when you cut off the graph, right, the edges and vertices, what's left has to be disjoint set of disks, right? Each component has to be homomorphic to a disk, so those are called the faces. And so here, this is a quadrangular embedding because every face is bounded by a 4 cycle or has degree 4. Let me mention here in this example, since we're on this slide, that this graph actually has cycle of length 3 this way, okay? So this is not bipartite, it has chromatic number 3. But on the plane, of course, we know every quadrangulation is bipartite. But once you get onto the surfaces, you can have quadrangulations which requires 3 colors or even more colors, okay? And here, this is a so-called triangular embedding of K6. 6 vertices here pairwise adjacent. Every face is bounded by triangles, so this is called a triangular embedding or a triangulation. Of course, the chromatic number of this graph is 6. Okay? Okay, so this slide explains surfaces, graph embeddings, and colorings. Now, of course, when we talk about graph colorings, perhaps the most famous problem is the so-called four-color problem, right? Many, many years ago. And this is about planar map. Of course, the original statement is about coloring the faces properly so that adjacent faces receive different colors. But you can define the do map, right? And so this is equivalent to the vertex version. Well, of course, the four-color problem was turns out to be a very difficult problem. But then it turns out that if you extend this problem to graphs embedded in general surfaces, it actually becomes simpler. So again, here a map is a graph embedded in a surface. And here we actually allow parallel edges in general loops when we deal with countings. But what's important is that each component is a simply connected region, a face. So a natural extension of the four-color problem from the sphere or the plane is to the general surface. And maybe I should mention here, define the so-called Euler characteristic, right? See here. So for any map, we have this. If a map has V vertices, E edges, and R faces, or sometimes called regions, then this is a constant called Euler characteristic. And for the orientable surface of genus G, C is equal to 2 minus 2G. And for non-orientable surface with K cross caps, okay, then C is equal to 2 minus K. And sometimes people just define 2 minus C, denote that by gamma. I just call this as the Euler genus for convenience, okay? And so he extended the map coloring problem, from the sphere to the general surface, and he proved this band, right? Shows that for every map M on the surface of, Euler characteristic C here, its chromatic number is always bounded by the floor of this thing. And it turns out that the proof is actually quite easy for this upper bound, just using the Euler's formula. And of course, you can replace C by 2 minus gamma, equivalently is this, okay? And now, of course, this bound, if you substitute gamma, by 0 here, then you get 4 here. But then that's really the four-color theorem. That's actually the difficult one, right? But off the plane, this upper bound actually is much easier to prove, okay? Just one-page proof. Of course, this band is not sharp, it's not tight for the claim bottom, okay? For the claim bottom, if you substitute gamma by 2 here, or C by 0, but it's not sharp, okay? The band is actually 6, okay? First proved by Franklin many years ago. And then other than that, this band turns out to be sharp. That's the very famous Map Color Theorem established by Ringel and Youngs in 1969. That's a big result back then. And the proof of this is, of course, to show that complete graph on n vertices can be embedded on a surface of this, Euler genus, which makes this sharp. And the chromatic number is exactly n here. Okay? It takes it took a lot of effort. Okay, so now, because they established this sharp band by showing that the complete graph can be embedded in a surface of this Euler genus. So you can see that the chromatic number and embedding are sort of closely related, right? And so another natural question here is that not only asking whether a given graph G can be embedded on a given surface, you can ask the following counting problem, right? Given a graph G and a surface, say orientable surface for simplicity for now, S sub G, how many embeddings are there? Right? Let's count. Not only just, is there an embedding? Now we ask exactly how many embeddings? Could be 0, could be 1, and so on, right? So now, of course, before we answer this question, the first thing is to make sure we know how to do the counting, right? How do you distinguish two embeddings? Are they different or not, right? And the simplest way was first, introduced by Tat, so-called introducing a rooting of a map, okay? By specifying a vertex and an edge incident to that vertex. So basically just a directed edge, okay? And then we have the so-called rooted map. And Tat proved that by rooting a map, you totally destroy the symmetries, okay? The automorphism group becomes trivialized. So it makes counting much easier. You can easily distinguish whether two rooted maps are the same. So for example, if we look at, I have to be careful with the timing. Give you some examples. So we use B sub n to denote the one vertex graph with n loops attached. So this is B2. Okay, so if we just draw these two on the plane, equivalent on the sphere, are these two the same thing? Some people say yes, some say no, depends on the homeomorphism. Right? But if we look at the rooted version, right here, this is the root vertex, well, that's the only vertex, but if I choose this as the root edge, right, this loop, but you can choose the root edge this way or this way, and these are two different rootings. The reason is that if you look at the right side of this root edge, if you look at the right side here, this face, usually called the root face, it has degree 2. It's bounded by 2 loops outside. But here, if you look at the right side, the root face has degree only 1, so this distinguishes these two rooted embeddings, okay? These are treated as two different rooted maps, embeddings. Actually, on the plane, this graph has exactly these two different rootings, I think. So in general, given a graph G here, we use M sub G to denote the number of rooted embeddings of G on this orientable surface, okay, of genus G here. M is for map, usually. Another way of trivializing the automorphism group of the embedding is by introducing labels of edges. And so, okay, and so that's basically what another school of mathematicians, graph theorists, topological graph theorists do. So the labeled edges, say E1, E2, and E sub m, and for each edge, they distinguish two different ends, positive end. So basically, they just treat this as a directed graph, okay, labeled. And then there is a combinatorial way of describing the embedding on the orientable surface. It's the so-called rotation system, okay? So at each vertex, you just go around the edge ends, say in a positive direction, say counterclockwise direction. That gives you a cyclic permutation of those ends. And you look at all those cyclic permutations, it gives you a permutation of all the 2m ends, E1 plus, E1 minus, and so on. And it turns out to be an equivalent way of describing the embedding. And there's a close relationship, of course, between the number of rooted embeddings, here denoted by M sub G, and here we can call this labeled embeddings, okay, or using rotation systems. There's a simple correspondence in here. And this is well known back 19. And here is just a simple illustration of B2 embedded in the plane using the 4 ends rotation systems, okay? This corresponds to the permutation. This is just one vertex, so only one cyclic permutation here, okay? 1 plus 2, 2 minus, and 2 plus 2, 1 minus, this 4 cycle. But those are 4 different rotation systems. And on the torus, you have these 2 different rotation systems. You can see the twist, right? The crossing here, so 1 plus 1 minus here. Okay, so back to the question of counting the number of embeddings. This problem was first introduced, I think, around 1989 in this paper published in JCTB by Gross and his collaborators. They defined this sequence, they call this as the genus distribution of a given graph G. Okay, you just count how many embeddings. Now, of course, in general, obtaining such counting sequence, of course, is very difficult because a special case, right? Just find the minimal genus, right? Find the minimal G such that this is bigger than 0 is an anti-hard problem. So in general, of course, it's a very difficult problem. And also, as we mentioned earlier, the Map Color Theorem is equivalent to find the minimal genus of just the complete graph, right? So, nevertheless, Gross and his collaborators and some other mathematicians since 1989, they studied some simple families of graphs, such as bouquets or wheels, or some sort of ladders. These are very simple type of graphs because, as we see, this sequence usually satisfies some simple recursions. So from those simple recursions, one can obtain some interesting results. For example, they can show that the sequence is, unimodal, even strongly unimodal. Well, that's the same way as saying it's log concave. And they actually give a conjecture in that paper saying that for any graph G, this genus distribution is log concave. It's a very strong statement. It's still open until today, and I don't think any kind of example has been found. Right? So in a certain sense, this is similar to, well, I shouldn't say similar, but there's an analog to the chromatic polynomial. Look at the coefficients. That's log concave. That was a difficult conjecture, was only proved several years ago, right? And there's a smaller conjecture about the genus distribution of bouquets by Stoll. Now, of course, Stoll's conjecture is more about the so-called the region distribution. Okay, because of the Euler's formula, the genus G and the number of faces or regions are related by this simple relation. So you can also talk about the region distribution, just by focus on the number of regions, right? The connection is this. If we use b, little b, to denote the number of embeddings with, say, that many regions, then the conjecture is, if you look at the mode where the maximum occurs of this number, okay, and the minim where the middle occurs, and Stoll conjecture that both the mode and the mean should be just one distance away from the this harmonic number. Either you round it down or round it up, okay? But this was only sort of resolved very recently, last year, by Cheng and myself, using some tools from analytic combinatorics and using the recursions. And it turns out that the conjecture is true for the meeting, but not really true for the mode. There are two cases. Okay, when n minus the floor of h sub 2n is odd, then the mode is the floor of this, so the conjecture is true. But if this difference is even, the mode may take the value of the floor minus 1. It's in two ways. So it's almost true, but not exactly. Okay, so I just would like to mention a little bit here that the proof, the starting point is, of course, using recursions of those numbers, okay? The b sub n r. And this recursion, for example, for the number of bouquets, right, embedding of the one vertex map, independently discovered by, Hale Zeger and David Jackson from CNO here, of course. And Jackson's proof of this recursion, of course, is by using the so-called rotation system. Okay, you can count the number of embeddings based on the number of ways you can factorize a permutation with a given number of cycles. So the recursion is not too bad. It's sort of linear with, of course, polynomial coefficients in the front and only has 3 terms. So you can play with this and show that the sequence is lower concave, proved in earlier 1990s. However, as I mentioned earlier, for some other simple families of graphs, such as wheels, or very close to wheels, or ladders, you can establish similar type of recursions. So from there, you prove the results you want. However, if you want to study more complicated family of maps, more dense, say, for example, cubic maps, okay? So every vertex has degree 3. And now, of course, we look at the whole family of cubic graphs, not just one individual one. And you can also define the so-called total number of embeddings. You can do the counting and series. Then it turns out that the recursion is much more complicated, and it's proved through much more advanced mathematics involving matrix integrals and those type of things. But nevertheless, again, Gould and Jackson, okay, from here, they established this recursion, okay? Well, h sub ng is just a simple normalization of c sub ng here, okay? Differ by a constant multiple, subject to certain boundary and initial conditions. But you can see that the recursion here, very impressive, okay? But much more complicated than this, right? This is nonlinear, first of all, and involves many, many terms. But it's still possible to make use of such a recursion and to prove some results, and that's what I did. Okay, I guess just appeared this year, so you can still show that the genus distribution is asymptotically normal, okay, with mean and variance. Again, those are through the tools of analytic combinatorics by looking at the generating functions and study those recursions. And one can also obtain the asymptotic results if you want, okay, for ng in a certain range. I'll mention this kind of results actually in general is quite difficult. Usually we can get results for c sub ng for bounded g, when g is a constant, okay, 1, 2, 3, up to 100. But when both n and g goes to infinity, usually this kind of asymptotic formula is not easy to obtain. Yeah. So this kind of results actually people are interested, let's see, people doing quantum physics, quantum gravity, they are interested in this kind of thing. Okay, so this is about embedding, okay? So that's sort of my first half of the talk today. I'm not sure if there's any questions so far. If not, let me just jump to the second topic, the chromatic number, okay? So we saw earlier that on a given surface, there are maps which require, or whose chromatic number is quite high, right? Behaves like square root of the Euler genus, right? According to the Map Color Theorem. But the natural question is that maybe those kind of maps which has large chromatic number is very rare, not many of them, okay? If you look at a typical map, say random map of large size, maybe the chromatic number is relatively small, only 4 or 5. It turns out that's true. That is true on any given surface, okay? The genus could be 100 or 1 million. As long as it's fixed, you look at the large random map, the chromatic number is highly concentrated on only a few numbers, 4, 5, 6, or 3, 4, 5. So that's the topic of the second part here. Okay, so if you look at, here, whenever we talk about random map, we mean it's uniformly at random, okay? So what's the chromatic number of a large random map? Okay. Now, of course, we know that if you talk about vertex coloring, then vertex coloring of a general map can be easily reduced to that of triangulation, right? You just subdivide each face, okay? So if you like, you can focus on triangulations. But of course, in terms of the probability spaces, of course, these are two different questions because different probability spaces. And now the four-color theorem, of course, tells us that on the sphere or the plane, the chromatic number is at most 4, okay? But what's the probability that a random planar map has chromatic number smaller than 4, say 3? Well, it turns out that approaches 0. It turns out that probability a random map has chromatic number 4 is equal to 1. The reason is that a random planar map with high probability, or high probability simply means that the limit as the size of the map and goes to infinity, the probability approaches 1. That's what we mean by high probability, okay? It's known that with high probability, it doesn't matter if you look at the space of all maps, or if you look at the space of just triangulations, then a random map contains many copies of this K4, okay, with high probability. If it contains K4, of course, the chromatic number is 4, right? You cannot color it with 3 colors. So actually, we have this on the plane, given the four-color theorem. So just the chromatic number of a random map on the plane just has 1 value, just a 4, okay? But what about off the sphere, torus, double torus, or orientable surface of genus G? Well, then in earlier 1990s, actually, that was when I was still here as a postdoc, okay? So I was one of the referees for Thomason's paper, reference paper about 5-calorie maps. So Thomason proved that on any given surface, okay, it doesn't matter if it's orientable or not, but it's a given surface. If it's locally planar, what do we mean by locally planar? It simply means it does not count short non-contractible cycles. Okay, all non-contractible cycles have to be long enough or bigger than a constant, depending only on the genus. Okay, so intuitively it means that if you walk along the graph, if you want to get the non-planar piece, you have to go further away, right? Non-contractible cycle only appear when you go further away. So such maps are called locally planar. Now, of course, actually, there are 2 notions about to quantify locally planarity. One is the so-called edge width, the one I just mentioned. You look at the shortest non-contractible cycle in the graph. It has to be large. Another definition is using the so-called faith width. That's another name for the so-called representativity, which is the number of intersections of any non-contractible curve on the surface with the graph. Okay? Of course, for triangulations, the edge width and face width are exactly the same thing. No distinction. But in general, you have edge width is bigger than or equal to the face width. Okay, so let me remind you of this definition here. So a map is called locally planar, let's say if the face width is sufficiently large, okay? Then, of course, edge width is also sufficiently large. Now, again, in earlier 90s, Robertson and his student, Vitre, actually, they had a paper showing that if a graph is if an embedding is locally planar, then it shares many properties with planar maps, okay? For example, the embedding is unique on the surface and blah, 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 a bunch of other properties. And of course, later along, then the famous graph minor theory by Robertson and Seymour about. But come back to the coloring. 1992, Thomason proved that if a map is locally planar, then it is 5 colorable. Okay, so the chromatic number is at most 5. And then we have of course, I should mention here Fisk, 1977. He constructed many locally planar triangulations on any given surface, okay, which require exactly 5 colors. So the chromatic number is actually equal to 5. So in the sense that you cannot go down. Okay, you cannot say that locally planar map is 4 colorable. That's not true. However, it may still be true that, the locally planar maps here or triangulations here are very spatial, okay? They're still a very tiny portion among all the locally planar maps. That's still a possibility. And so now it comes back to a result we proved earlier, actually, when I was still a postdoc maybe, I wrote that paper. But published in '94 with Ben and, again, Bruce Richmond is a faculty member here, okay, with whom I did my postdoc. So what we proved is that on any given surface, almost all maps are locally planar, okay? In terms of the random map language, it means with high probability, a random map is locally planar. So with high probability, we don't have to distinguish all maps and locally planar maps. They're the same. They're asymptotically the same, okay? Well, that combined with Thomason's coloring result then shows that on any given surface, okay? So non-planar to be more interesting, right? Then the chromatic number is either 4 or 5. It's at most 5. It's at least 4 with probability 1. So only 2 possible values, okay? Even though on a given surface, you may have some maps which require very high, right, number of colors to color, right? If the genus is very high, say 1 million, then you require square root over 1 million, that many colors, huge. But if you look at a random map, 5 is the upper bound. We actually made a conjecture in that paper saying that you can narrow this down to 4. But it seems to be difficult to prove or disprove this, right? Because of the Fisk's construction I mentioned earlier. And actually, as the time goes by, I become a little bit suspicious about this statement. Okay, maybe the probability of 5 here is not 0. And, well, there's reason for that. So I will come to the next one. So this is about triangulations or maps. Now, what about some spatial families of maps? Let's look at quadrangulations. or so-called even embeddings, okay? Embeddings in which all faces have even degrees, okay? Of course, even embeddings, the coloring of even embeddings can be reduced to colorings of quadrangulations because you can quadrangulate each even face, okay? In the way similar to subdivide a general face to triangulations. So if we look at even embeddings, or more specifically, say, quadrangulations, what's the distribution of the chromatic number of a random quadrangulation, say? Now, on the plane, it's very easy, right? We know it's bipartite, so the chromatic number is 2. But as you saw earlier in our first slide, off the plane, you may have quadrangulations which contain odd cycles. Of course, those odd cycles will have to be non-contractible, okay? Either going around the cross cap or going around the handles, all right? So which may require 3 colors. So there are some analog results to general embeddings, chromatic general embeddings. For example, Hutchinson, 75, she showed that this band is similar to the Hilbert band for the chromatic number of a general map, right? But this is a little bit smaller here. And this is also sharp if the surface is not the Klein-Bottle or double torus, okay? So in general, so it means that if you have an even embedding or quadrangulation, the chromatic number can still be very, very high, okay? It's the same as 16 times the Euler genus or times k. So it can still be quadratic in the genus, okay? But if you look at the random quadrangulations, the chromatic number turns out to be, first of all, Hutchinson proved, 95, okay, after Thomas proved the general 5-coloring theorem for general maps, and she did the similar thing for locally planar quadrangulations. And she proved that locally planar quadrangulation, or in general, even embeddings, is 3-colorable. Okay? 3 colors is enough, as long as the map is locally planar. Well, so I had a paper earlier, that's just enumeration. I can count the number of bipartite quadrangulations on a given surface and the total number of quadrangulations. So I have a formula, and then you just take the ratio. It turns out that the probability that a random quadrangulation is bipartite, has chromatic number 2, the probability is 1/2 to the power of Euler genus, gamma, which is 2 minus the Euler characteristic. So you combine this result with Hutchinson's result, which shows that there are 2 non-zero probabilities for the chromatic number of a random quadrangulation on orientable surfaces. Okay? Chromatic number equal to 2 with this probability. Okay? Equal to 3, this probability, just 1 minus that. Okay? On the sphere, of course, gamma equal to 0, so 100% it's bipartite. But on the projected plane, here's orientable surface. On the torus, right? On the torus, Euler genus is equal to 2 times the number of handles. This is 1/4, this is 3/4. Okay? So at least here you can see that there are 2 non-zero values here in the distribution, right? It's not just one single value. There are 2 for orientable surfaces. Now, what happened to non-orientable surfaces? The simplest case, of course, is the projective plane, N1. And then there is a result. Well, next slide, but let me mention this result first. On non-orientable surfaces, say N sub k, Fisk and Moha, they had this similar result, saying that always 4 colorable. So you increase the number of colors by 1, right? From 3 colorable to 4 colorable for quadrangulation. Again, for general map, you need 5 colors. That's Thomason's result, okay? For even embeddings. And for general maps, there was no distinction there between orientable surface and non-orientable surface, 5 colors. But here, there's a distinction between orientable surfaces, which only requires 3 colors, and non-orientable surfaces, which may require 4 colors. But what is the actual probability distribution of the chromatic number of a random quadrangulation on n sub k, non-orientable surface? Well, again, okay, so here we look at the simplest case, N1, the projective plane. There's an earlier result here, right, by Youngs. He showed that on the projective plane, a quadrangulation, the chromatic number of a quadrangulation is either 2 or 4. Okay, there's no 3. Either it's bipartite or its chromatic number is equal to 4. Okay, only 2 possible values. Of course, this 4 also comes from that Hutchinson's bond, okay, similar to Hewitt's bond. So either 2 or 4. Interesting enough, and the proof actually was not too difficult, just 1-page argument using parity. But of course, there are different characterizations of what kind of quadrangulations require 4 colors and so on. We're talking about locally planar, and there's this characterization and second characterization here by Mohan and Seymour. And this is the one we can actually use to do some counting. This is something currently I'm working with Jen Gao, and I think we can prove the result I'm going to state in the next slide. So basically, Mohan-Seymour's characterization is the following. So you take a quadrangulation on n sub k, okay? Now, of course, we're talking about locally planar, so the phase width is large enough, okay, or the responsivity is large enough. Then Robson-Seymour's graph minor results imply that such a quadrangulation contains those non-contractible cycles, C1, C2, C sub k, such that if you cut this off, you have something here, inside here, that this is in the projected plane, okay? Or you can think of this as a Mobius band, if you like, if there's a hole outside. So you have K cross caps in here. You can think of those as near quadrangulations on the projected plane, okay? Those are the face degree of the root face. And then after cutting off those, what's remaining is the planar piece. We denote that by Q sub 0 with a bunch of distinguished faces here, which are possibly non-quadrangular. Okay? Other faces here are quadrangular. And the characterization says that such a locally planar quadrangulation is or requires 4 colors. First of all, they are all 4 colorable, according to Mohan, the fixed theorem, because locally planar, always 4 colorable. Now, it does require 4 color if and only if, so that's a very nice criteria here, if and only if odd number of those, right? We have K such things here. All of those are non-bipartite. Some of those near quadrangulations on the projective plane may be bipartite, may be non-bipartite, okay? But if all number of those are non-bipartite, then the chromatic number of the whole thing has chromatic number 4, okay? Otherwise, the chromatic number is less than 4, it's 3 or 2, okay? So using this characterization, one can come up with this conjecture. Actually, this conjecture sort of dates years back, okay? 2008, there was a conference in Yokohama, okay, in honor of Nagami, I think. So I gave a talk about chromatic number of random quadrangulation at that time. And after my talk, Mohan and Nakamoto independently wrote to me saying that, I think this is true. Right? They both think this is true and give some reasoning, basically related to the previous slide comment. They say, the chromatic number of random quadrangulation equals to 4. This probability is exactly 1/2. Okay? But then again, this is known. This is according to my earlier paper back to 93. And this is the remaining case, of course, since it's 1/2 minus that. So now, all of a sudden here, if you look at the random quadrangulation on non-orientable surfaces, the distribution of the chromatic number, now there are 3 non-zero values in here. Now, of course, the spatial case, when k equals to 1 on the projected plane, when k is equal to 1, the middle line here, this is equal to 0, okay, in agreement with Fisk's result, or Young's result, to be more precise. Okay, perfect. I think I have 4 more minutes. Any quick questions here? And as I mentioned, so we believe we can actually settle this. So it's work going on with Jin, using this criteria here and doing some enumeration, doing some counting. Okay, you just need to count how many such quadrangulations are there, such that all number of them are non-bipartite. So, because I have 4 more minutes here, so let me might as well mention there's another connection here about so-called Eulerian triangulation. Okay, so we know what a triangulation is. Every face is bounded by a triangle. And in general, locally planar triangulation requires 5 colors. Okay. But what about Eulerian triangulation? It means that every vertex has even degree. Okay. Now, there is a close connection between chromatic number of Eulerian triangulation and quadrangulation, or even embedding in general. Right? If you just look at the quadrangulation, for example, you just subdivide each quadrangular face, right? Insert the vertex inside each quadrangular face and connect to every vertex on the boundary. You get a triangulation, right? And every vertex has even degree, so that becomes an Eulerian triangulation. Okay? So there is such a simple connection between the chromatic numbers of Eulerian triangulation and the quadrangulation or even embeddings. Now, on the plane, of course, he would prove that planar triangulation is 3-colorable if and only if it's Eulerian. So that also makes the Eulerian triangulation very spatial. And then 2002, Hutchinson, Richter, again, Richter is a faculty member here. Seymour, they showed that locally planar Eulerian triangulations is 4-colorable. Okay, so 1 less, right? In general, requires 5 colors according to Thomason's result. But if it's Eulerian, 4 colors. Okay. Now you can see how this is just exactly 1 more than the chromatic number of locally planar quadrangulation, right? You subdivide each quadrangular face, basically you just increase the color by 1. So with this connection, it seems that one has this, oops, sorry. Did I should go, so yeah, just show you this slide here. So it suggests this. The distribution of the chromatic number of random Eulerian triangulation, again, has those 3 possible values, but increased by 1. Instead of 2, 3, 4 for quadrangulation, now for Eulerian triangulation, the chromatic number is 3, 4, 5 with the same probability here. Okay? Seems possible. I think I should, this is a good time to stop here. If you have any question, please feel free to ask.
Any questions?
Hi. So if you go back to the question on embedding, the two examples you showed were the bouquets and the cubic, and the mean for both of them were around logarithm.
Log n, yeah.
And do you have example of family where it's far away from that? Like, seems like
That's
plausible.
an excellent question. No, actually, this seems to be the general phenomenon.
Yeah.
Yeah, it's around log n.
Yeah.
Yeah.
Thanks.
Thank you. So in the earlier slides, there were a definition of the rotation system,
Rotation system.
for counting.
Yeah.
Is it well defined for non-orientable surfaces?
Well, that's, again, another excellent question. If you want to describe non-orientable embeddings, then you need something extra, okay? Not just those two MNs and the rotation system. Because now you need to, because there's no orientation, I mean, there's no uniform orientation, right? So basically, you need to look at, for each edge, not only you need to look at the positive ends and the negative ends, you also need to look at positive side and negative side. So for each edge, you introduce 4 objects, okay? You look at the permutations of those 4 things, and the right terminology is they call there's a book by Thomason and Moha, right? Combinatorial description of those embeddings. There's a word so-called signature. You have to look at the signature of this edge. Yeah. So there's one extra level if you want to deal with non-orientability. Yeah.